Hello everybody, how's everybody doing? CRS here. In this video, we will be covering all those questions that are most probably going to occur in your final exam from the chapter Ray Optics. This is a prediction series, so hook on to these videos. Let's look at the first question. The first question says, an air bubble in a cube of glass of side 21 centimeter appears to be at a depth of 10 centimeter from one face and 4 centimeter from the other face. Find number one, the actual depth of the bubble from the first surface. That's the first question. And the refractive index of the glass. Let's try to understand this question. Let me first draw out the cube. So here is the cube. It's a cube of an unknown material. So let me just paint it this so that we can imagine it to be some material. And then we will also say that at some place inside there is a bubble. So here is a bubble. Let me give it another color. Let's say I give it some other color, maybe blue, right? So that's the bubble that's there inside. Quite a big bubble. Maybe this is good. All right. So that's the bubble. Now, when you see from the first face, so let me call this face 1. When you view it from here, this same bubble does not appear where it is, but it appears at a different place. Where does it appear? It appears somewhere here, right? And when it is viewed from the other face, it appears somewhere here. So when you view this bubble, when you view this bubble from this face, it appears to be normally shifted to this side, and when you view it from this side, it appears to be normally shifted here. That's what the question says. Now let's write down all the data. Well, do you see that the question says that the side of the glass is 21 centimeter? Now maybe I'll label that. So this distance, my dear friends, happens to be 21 centimeter, and it appears to be at a depth of 10 centimeter. So from here to here, the question says that it is 10 centimeter depth and 4 centimeter from the other face. If you look at what is the depth from this face, from here, the depth happens to be 4 centimeter. My question is, what is the actual depth of the bubble from the first phase? So this is phase 1, and my friends, this is phase 2, and we need to find what is the actual depth of the bubble. So let's say that the actual depth of the bubble from the first phase is x. We know that let's assume that the refractive index of this material is mu 1 and this is mu 2. This is basically, or maybe I'll just call it mu d, denser medium, refractive index of the denser medium. This is mu r, denser, rarer medium's refractive index is mu r, which is the surrounding medium. We will now write an expression relating real depth, the place where the bubble really is, to apparent depth, the distance to the place where it appears to be. So the refractive index of the denser medium with respect to rarer medium is equal to the ratio of real depth to apparent depth. That's the formula. When we know the formula, you can simply write down for two cases. In this particular case, I shall write for phase 1. For phase 1, the refractive index of the material with respect to the surrounding medium, denser medium with respect to this is denser, this is rarer, denser medium with respect to the rarer medium, is real depth. Real depth, my dear friends, is x, and apparent depth is 10. So let me just write that as 10. This is our equation number 1. Okay, let me put that in a box. So this is our first equation. Alright, so there we go. That's equation number 1. Similarly, you can write another equation for the phase 2. Real depth is all the way from here to here. If this is x and that's 21 centimeter, this is supposed to be 21 minus x. So this is x. This distance is definitely going to be, so let's say that this distance is definitely going to be, all right, there we go. All right, that distance is definitely going to be 21 minus x, right? So for phase 2, the refractive index of the denser medium is the same denser medium with respect to the rarer medium. Now happens to be 21 minus x divided by the distance now is 4. The question says from the other side it is 4. Well, that becomes your equation 2. So this becomes your equation 2. Let me put that in a box. And that's equation 2. Do you see that LHS and RHS, I mean LHS on both the equations, both the equations are the same. You can just equate the RHS. When you equate the RHS from equations 1 and 2, you have x divided by 10 equal to 21 minus x divided by 4. You can cancel this out and cross multiply. You will have 2x equal to 105 minus 5x, by the way. Transfer the 5x here, you get 7x equal to 105, or x would be equal to 15 centimeter. So x, my dear friends, is 15 centimeter, which simply means that the real depth, the actual depth of the bubble from the first phase is 15 centimeter. Going further, we also have to find the refractive index. I think we have answered the first question. Refractive index of glass. So glass's refractive index with respect to that of air, because nothing is mentioned, I'll assume that it is air, mu dr would simply be equal to one of these equations, please. Mu dr is x divided by 10. X is anyway known, so we can write 15 in place of x divided by 10. So the answer turns out to be 1.5. Refractive index does not have a unit, so we will stop it there, and that's your final answer as well. So this becomes your final answer, right? X is 15 and refractive index is 1.5. Let us look at the next question. A small bulb is placed at the bottom of a tank containing water to a depth of 1 meter. So, from the given data, you can say that the depth of the bulb under the water surface is 1 meter. Find the critical angle for water-air interface. You need to find the critical angle for the water-air interface. Also calculate the diameter. Of the bright patch of light on the surface. So we will call that capital D, right? We will call that capital D. We need to calculate the diameter. Of course, if you just found the radius, that would be good enough. Double the radius would be diameter. Now let us imagine this. Well, let's imagine that there is a water surface, right? So here is the water surface, and you have put a bulb there. So let's assume that you put a bulb here. Okay, that's a bulb. The depth of the bulb, the depth of the bulb is 1 meter. So let's just write that maybe from here to here, the depth of the bulb is 1 meter. That's what is D, by the way. Right? That's D. So if you can imagine, light will go out of this particular interface and then get out. But then if the angle of incidence is greater than the critical angle, then light will come back to water. This is water, that is air. Now if you can imagine, there is going to be a cone of light that is going to be incident on the interface. Those rays of light which are which are incident at the critical angle will graze the surface of the two media. If the angle of incidence is lesser, they will go out, and if it is greater than the critical angle, they will go back in. So that is the understanding. So let us imagine that there is a cone of light that goes out. So there is a cone, right, of light that goes out, something of this sort. Right? I will imagine this starting from here. So that's a cone of light that simply goes out. We can make it look a little bigger. That'd be quite convenient. So let's do that. So here, my dear friends, is where your interface is. So that's your, okay, fine. So this is the interface, water and air. Let me draw the normal here. That's a normal, my dear friends. And then maybe we will imagine that one ray of light goes straight up, okay, and the other ray of light is going this way. One ray of light goes this way and the other goes this way. This ray of light is incident at the critical angle, so I shall draw that angle to be C. That's the critical angle. Those rays which are incident at an angle lesser than the critical angle will go out, and those rays of light which are incident at an angle greater will go inside water back again. So we need to calculate this diameter. Let me call this the radius R, and the depth of the bulb is B. Because this is C, this is also C. They are alternate interior angles for that matter. It's quite easy to solve the question now. We will find the critical angle. We know that the refractive index of water with respect to air, denser medium with respect to rarer medium, is simply equal to 1 divided by sine C. Right? You can interchangeably use n and mu. This time I have used n. It does not make any difference. So refractive index of water is given in the question. It's given to be 4 by 3. So let us write down 4 by 3 equal to 1 divided by sine C, my dear friends. So sine C would simply be equal to 3 divided by 4. C would be sine inverse of 3 by 4. Okay. And sine inverse of 3 by 4 turns out to be 48 degree 35 minutes. That's the critical angle. So any ray of light that is incident at an angle of incidence greater than 48 degree 35 minutes will undergo total internal reflection. Any ray that is at an angle of incidence less than that will go outside water, air. Will go outside water to the air. Now, having said that, let us, I think we have found the first thing, which is the critical angle. Let's also find the diameter, a simple triangle problem. We have tan C, my dear friends. Tan C is opposite divided by adjacent. Opposite is radius and adjacent is depth D. You need to find the radius, so it will be D tan C. D is anyway 1 meter and tan of 48 degree 35 minutes, my friends, becomes equal to 1.134 meter. So that is the radius. Once you know the radius, it's quite easy to calculate the diameter. The diameter is twice the radius, so D would be equal to 2.268 meter. Now that becomes the answer, right, for the final. Okay, I think here we go. Just wanted to put a box. There it is. So this is the answer for the diameter, right? Maybe you can simply write it as capital D because I used capital D. Small d is for the depth. Okay. This is how you would solve any question that is based on critical angle and total internal reflection. Let's go to the next. Let us look at the next question. A point object is placed at 50 centimeter from the surface of a glass sphere of radius 10 centimeter along the diameter. Where will the image be formed after refraction at both the surfaces? That's the question. Let us imagine the question. First, there is a sphere. Let's assume that this, my dear friends, is the sphere and I shall paint it blue. And then we will draw the principal axis. Let's say that this line is the principal axis. It also forms the diameter as a part of this line. Going further, you can choose an object somewhere here. Let's say there is an object out here. A ray of light from the object now starts out and is incident. It starts out and is incident on the glass sphere, something like that, right? That's a ray of light. It is incident on the glass sphere. That's the first surface. And for that surface, for this refraction that is going to occur, let's say the pole is here, and let me call that pole P1, right? That's the pole. And after this, it will undergo refraction. It will bend, and probably it will go something like this. It's going to go something like this. It's going to undergo refraction at the second surface. But in case if it does not, then, my dear friends, the ray of light, if in case it did not undergo refraction and the medium of glass had continued, then the ray of light also would have continued something like this. The ray of light also would have continued and probably had formed an image there. Let me call that image I dash. It is an image that does not form, and that's why I have called it I dash, because the ray of light is certainly going to bend at the second surface and the final image forms here. That's where the final image forms. Let me call that image I. The ray of light has traced this path. So we know the refraction is happening at two surfaces. One surface has got pole P1, the second surface has got pole P2. Let us assume that the refractive index of the surrounding medium is air. I'll call that N1, or yes, of course N1, and that refractive index is 1. The question has given us the refractive index of glass, and that's 1.5. We know that this is object distance. From here to here, that's object distance. We'll call that U. And that's the center. Center is here. You can say that this is the radius of curvature. I'm sorry. So we can say that this is the radius of curvature. Let me call that R. The radius of curvature is R. For the first refraction, we shall write an equation. For the first refraction, the object is O, my dear friends, and image is I dash, because the refracted ray goes straight and intersects the principal axis there, because we can only do one refraction at a time. Let us take up the formula. What does the formula say? It says refractive index of the image medium divided by image distance minus refractive index of the object medium divided by object distance equal to difference in refractive indices divided by radius of curvature. That's the formula. Now, what is an object medium? Object medium is the medium in which the incident ray lies. So the incident ray is here. And that's the image medium for this refraction. For refraction at pole P1, the incident ray lies in air and the refracted ray lies in glass. So the refractive index of the image medium is 1.5 and refractive index of the object medium is 1. So let us write this down. Let's substitute. Refractive index of the image medium is 1.5 divided by image distance. My dear friends, in this case is this distance all the way from the center, all the way from the pole, to that place. This distance is what I would like to call V dash. That's the image distance. So I just manipulate this formula, call that V dash. 1.5 divided by V dash. V dash is a distance measured from this pole and it is being measured in the direction of incident light. But it's an unknown. You must not worry about its sign convention. Well, minus N1 is the refractive index of object medium. I shall write 1. Object distance has been given to you, my friends. The question says that the object distance is 50 centimeter. That's 50 centimeter. Question says 50 centimeter from the surface of the glass sphere. So here is the surface of the glass sphere. From there, it's at a distance of 50 centimeter. I shall write that down. 50 equal to difference in refractive indices. 1.5 minus 1 is 0.5 divided by radius of curvature. One must be very well aware of sign convention. Now when you write U, my dear friends, U is an object distance. It is measured from the pole. When you measure it from the pole, you have to measure that distance in the opposite direction of incident light. So both U, which is 50 in this case, will pick up a minus sign. Minus into minus will become plus. Right? And the radius of curvature is measured from the pole as well. From the center of from the pole, if you head towards the center, see, you are going in the direction of incident light. Incident light is going from when I face the board, the incident ray is going from left to right. So any direction that you measure from the pole in the rightward direction in this case is positive. Any distance that you measure in the leftward direction is negative. When that is the situation, you can say that U is negative, and that's why minus into minus has become plus. R, my dear friends, is positive because from the pole towards the center is in the direction of incident light. I shall write that positive 10. I think we are all set to find V dash. we have 1.5 divided by V dash plus 1 by 50 is 0.02 equal to 0.05, my dear friends. And 1.5 is 3 divided by 2 V dash, that's equal to, you send this here, it becomes 0.03, by the way. 3 ones are, this becomes 0.01, and you take the reciprocal, 2 times V dash, 2 times V dash would become equal to 100, or V dash would become equal to 50 centimeter. So that means the image from this pole forms at a distance of 50 centimeter. That's where the image would form if only one refraction took place. But there is not just one refraction taking place. Another refraction also takes place at another pole, which is at a distance of 10 plus 10, 20 centimeter from this pole. So for that refraction, this is the incident ray and that is the refracted ray. When the incident ray is extended, you get the object for the second refraction. So the image for the first refraction is the object for the second refraction. That's the trick to solve the problem. When that is the case, my dear friends, here is the object distance. The new object distance, I'll call it u dash if you like it. From here to here, that's u dash, my dear friends. And the final image distance is v. That's the final image distance from the second pole. Having said that, my dear friends, let me write the formula. Refractive index of the image medium. Now the image medium is where the refracted ray lies, and that is air. I'll call that N1. Divided by image distance, that's V. Minus refractive index of the object medium. Incident ray is where the object medium is, and that is glass. I shall write it as N2 divided by u is, my friends, whatever is the image distance, I mean whatever is the object distance in the second case, which is the image distance, which is the image in the first case, and that object distance, I'll call that u dash, and u dash, my dear friends, has already been written. From here to here it's 50, from here to here it's 20, so obviously u dash would become equal to 30 centimeter, because it's 50 minus the diameter, that's 20. So automatically you can write it as u dash equal to n1 minus n2, difference in refractive indices, divided by radius of curvature r. Let us substitute and get the answer. N1, my friends, is 1 divided by V. We do not know. You do not apply the same convention. N2 is 1.5. N2 is 1.5 divided by U dash. U dash, my friends, is 30 centimeter, but that distance is being measured in the direction of incident light. Hence it is positive. I shall just write 30 equal to N1 minus N2, which is minus 0.5. 1 minus 1.5 is minus 0.5 divided by radius of curvature. But don't you make a mistake. The radius of curvature must be measured from the new pole, and in order to get to the center to measure the radius, you have to go in the opposite direction of incident light, and hence it is, my dear friends, obviously minus 10. You are going this way to measure it. These minus signs get cancelled. Let us find out what you get. 1 by V, my dear friends, minus, this is 0.15 divided by 3 would be 0.05 equal to, this is plus 0.05, by the way. Transfer it there. You have 1 by V equal to 0.1, which implies the reciprocal V would simply be 10 centimeter. That is the image distance. So it simply means that the image will form at a distance of 10 centimeter, because it's a plus 10 centimeter. It means from the second pole, you need to go a distance of 10 centimeter, because there is a plus sign in the direction of incident light to get the image, to find the image thus formed due to these two refractions. Now that's how you solve problems using sign convention in ray optics. The other question that I would leave you with is, while you're deriving this formula, you apply the sign convention. But while you're solving the problem, you apply the sign convention once again. Please ponder about why do you apply sign convention twice. Let's look at the next question.
Let us look at the next question. The next question says the radii of curvature of two surfaces of a convex lens are 0.2 meter. So let me jot that down. I shall write R1, the radius of curvature of the first face, as 0.2 meter, and radius of curvature of the second face as 0.22 meter, as given in the question. The question to us is, find the focal length of the lens. We need to find the focal length of the lens if the refractive index of the material of the lens, I shall write it as NL. NL is the refractive index of the material of the lens. That's 1.5. Also find the change in focal length. We also need to find the change in focal length, right? We also need to find change in focal length. If it is immersed in water, if it's immersed in water of refractive index 1.33, right? So the first thing that we need to do is find the focal length of this lens in air. Let's do that. And then we will find the focal length of the same lens in water. After that, we can just find the change in focal length. It's as simple as that. For calculating the focal length, we need to know what is lens maker's formula. We have all derived it. So the lens maker's formula, my dear friend, says that 1 by f of a lens is equal to NLS, which means refractive index of the lens with respect to the surrounding medium, minus 1 multiplied by 1 by R1 minus 1 by R2. That is the equation which we call lens maker's formula. What is R1? Let's try and understand the question here. So here we have a lens, and that happens to be the principal axis of the lens. The radius of curvature of this surface, which forms an imaginary sphere, something of that sort, okay, has a center here, and the radius of curvature, let's say, is R1. So that's the optic center, and R1 is the radius of curvature, because we will assume that the light is going from this side to that side. All distances that you measured rightward in this situation, because you have assumed the direction of light to be incident light to be rightward, this distance R1, which is supposed to be measured from the optic center, in order to measure it, if you go towards the center of curvature, you will see that that distance is positive. And similarly, if you can imagine, there is the center of curvature of this surface. Let me call that C once again. Maybe this is C1 and this is C2. That radius of curvature is R2, measured from the optic center. Every distance is measured from the optic center. To reach there, you are going in the opposite direction of incident light. So that measurement is negative. You can now say that R1, my friends, is positive and R2 is negative. Sir, how do I decide which one is R1 and which one is R2? Whenever you consider the direction of incident light, it does not matter whether you consider it this way or you consider it that way, your answer is going to remain the same. To whichever surface light hits first, the radius of curvature of that surface is R1, and the radius of curvature of the next surface is obviously R2. Let us substitute it out here. We have 1 by f in air equal to NL divided by NA, because the radius of the refractive index of the lens is NL. It's given in the question. Initially it is kept in air, so that's why the lens's refractive index is being measured with respect to that of air. Minus 1 multiplied by 1 by R1 minus 1 by R2 is what you would write. Okay, I don't think we will need that C2 anymore, so we shall erase that, right? So we have 1 by R1 minus 1 by R2. Let us substitute now. 1 by FA is equal to 1.5, which is the refractive index of lens. That's 1.5. Refractive index of air is 1, so it's better not to write it. Then I have 1 minus 1 into 1 by R1. 1 by R1 is 0.2 minus of minus. There is a minus in the formula and R2 is negative. So minus into minus becomes plus. You have 1 divided by 0.22. Now that is the lens maker's formula for focal length of the lens in air. So 1 by FA is going to be 0.5 multiplied by 0.22 plus 0.2 divided by 0.2 multiplied by 0.22. When you work this out, my dear friends, the focal length of the lens in air turns out to be 0.29209 meter. That is the focal length of the lens in air. Now, a similar job can be done to calculate the focal length of the lens in water. How do you do that? Quite simple. Watch. Everything is the same, just that in previous case, the surrounding medium of the lens was air. Now it is surrounded by water, because the question says that find the focal length. We need to find the focal length of the lens, the same lens, when it is kept in water, of refractive index 4 by 3 or 1.33. That's what the question says. Now, when that is the situation, my friends, that has been given to us that it's 1.33. Let's jot the formula down. We have 1 by Fw, focal length of the lens in water, equal to NL divided by NW, the focal length of the, refractive index of the lens divided by refractive index of water, minus 1 into 1 by R1 minus 1 by R2, my dear friends. When that is the case, we have 1 by Fw equal to NL is 1.5 divided by NW, that's 1.33 minus 1 multiplied by 1 by R1. R1 is just 0.2, minus of minus becomes 0.22. Rest everything is the same as in the previous case, just that the surrounding medium has changed. When you work out Fw, dear friends, when you work out Fw, you will find that the Fw is 0.819. So the focal length has become longer. Before it was just 0.209. Now the same focal length has become larger. That means the rays of light were bending sharply when the refractive indices difference was high. 1 is 1.5, air was 1. So the difference is 0.5. Light was bending a lot. But now the difference has become lesser. The refractive index of glass is 1.5, that of the lens is 1.5, but the surrounding medium, my dear friends, is 1.33. Do you see the difference has become smaller? So the ray of light has bent less, because of which the focal length has become larger. Now, all that we have to do is find the change in focal length. Dear friends, the change in focal length delta F would simply be equal to Fw minus F air. Fw is 0.819 minus 0.209 must be equal to 0.61 meter. Now, that is the change in focal length. Quite easy to understand, and that's how you apply lens maker's formula with the sign convention. So let us look at the next question. Two lenses of focal length 0.2 meter. So the focal length of the first lens is f1 and it is 0.2 meter, and 0.3 meter focal length of the second lens is 0.3 meter, right, are kept in contact. So they are in contact with one another. Find the focal length of the combination. Let me call the combination's effective focal length F effective. We need to find that. Calculate the powers of the two lenses. So there are two lenses out here. We need to find each of their powers. P1 and P2 have to be found, and the power of the two lenses combination. The effective power also has to be figured out. So these are the questions thrown at us. Let's try to answer them one by one. Quite easy. Now, whenever there are two lenses kept in contact, then the effective focal length 1 by F effective becomes equal to 1 by F1 plus 1 by F2. This is the effective focal length of the combination. We have 1 by F effective, my dear friends, equal to 1 by F1. 1 by F1 is 0.2 meter plus 1 by F2 is 0.3 meter. Now, all that you will have to do is simplify this. We have 1 by F effective being equal to 0.3 multiplied by 0.2 divided by 0.2 multiplied by 0.3, right? Of course, there is a plus in the numerator. I'm so sorry. So we have effective focal length after simplification turns out to be 0.12 meter, and that is the focal length of the combination. Let us look at the next question. An object of size 2 centimeter. So the height of the object is given to us. So let's write the height of the object HO as 2 centimeter, right? That's given in the question. Is placed at 20 centimeter in front of a convex lens. So the object distance from the lens has been given to us. That's 20 centimeter. We will bother about the sign convention in a while. A focal length 0.15 meter. Focal length of the lens has been given to us. 0.15 meter is 15 centimeter, right? So we will write 15 centimeter. Find the image distance and also the size of the image. You have to find the image distance and the size of the image. HI has to be found. So let us try and understand this question. Well, here is a lens. So I put a lens here, and let's draw the principal axis, by the way. So this happens to be the principal axis. That's the principal axis. and here is the optic center, that's the optic center O. The question says, let's also mark the focal length approximately exactly this much from here to here, maybe a little far away, fine. So that's the focal length on either side. I have an object that's at a distance of 20 centimeters. So there is an object here at 20 centimeter. If you want to draw rays of light, maybe you would want to do it like this. One ray of light goes this way. It passes through the focus. The other ray of light passes through the optic center and forms an image here. Both of these rays of light converge at this point, right, and then form an inverted image here. This is quite something that must happen in your head. A ray diagram has been drawn here only for simplifying the situation. This need not be drawn in the exam. So the object distance is this, all the way from the optic center to place where the object is, and image distance is from the optic center to the place where the image is, right? Now we will decide on the sign convention. See, the rays of light are coming in this direction, so that direction is positive. Any distance that you measure from the optic center in the rightward direction, that's positive. Any distance that you measure in the leftward direction is negative. So it's quite obvious that the object distance u is negative, right? We will put that minus sign. V is positive. So should we put a positive sign there? No, you should not worry, because it's an unknown. If it's an unknown, don't worry about it. And then we have to find the focal length also. A parallel beam of light that's falling on the lens would converge to the focus, and that convergence happens towards the right of the lens, and the focus is here. The principal focus is there. That's the focal length, by the way. So that distance is measured from the optic center in the direction of incident light. Hence, this also is negative. Any distance measured above the principal axis, that's the height of the object, and that turns out to be positive because it's a distance from the principal axis measured above it. Having said that, quite easy to crack the question now. We know the lens formula. The lens formula says that 1 by f, my dear friends, is equal to 1 by v minus 1 by u. That's the formula. Well, let us substitute. We have 1 by 15 equal to 1 by v. We do not know. Minus of minus becomes plus, and we have 1 by 20. Let's move this 20 to this side. You will have 1 by v equal to 1 by 15 minus 1 by 20. For simplification, you can definitely pull out 5 as a common factor, and you will have 1 by 3 minus 1 by 4. Okay. And this is, after simplification, going to be 1 by 60. That's 1 by v. Now what does v become equal to? V becomes equal to 60 centimeter, because we substituted in centimeter. Let's interpret this answer. We've got a positive 60. The image distance is positive 60 centimeter, which means that the image is going to be found at a distance of 60 centimeter from the optic center. So that's what it says. Image is found at a distance of 60 centimeter from the optic center. You've got a plus sign, which means you must go in the direction of incident light to find it. Had this been negative, you should have gone in the opposite direction to a distance of 60 centimeter in order to find it. Now it's positive. So you must read and interpret the answer like this. The image is formed at a distance of 60 centimeter from the optic center measured in the direction of incident light. See, it's here, in the direction of incident light, 60 centimeter from the optic center. That's how you interpret the answer. Going further, we also have to find the size of the image, which is hi. Dear friends, the magnification is defined as v divided by u for a lens, and magnification is height of the image divided by height of the object. That's equal to v divided by u. You want height of the image would be equal to v divided by u multiplied by height of the object, by the way. So v, my friends, is 60 divided by u is minus 20 multiplied by 2 centimeter. This will go away, and that becomes 3. 3 2s are 6 centimeter with a minus sign would be the height of the image. What it means is that the height of the image is 6 centimeter. So that's 6 centimeter height of the image, and negative sign tells you that it is measured in the direction or maybe below the principal axis. That's how you should say it. the minus 6 centimeter tells you that the image is 6 centimeter long and its height is measured below the principal axis. Hence, you can say it's an inverted image. It's an inverted image. The rays of light actually meet, so it's a real image. It can be caught on a screen. It's a real image. It's an inverted image because the magnification is a number greater than 3. I mean, greater than 1. It's 3. See? V by U is magnification. Turns out to be 3. That means the image is going to be 3 times bigger. It's a negative sign. That simply means that it's going to be inverted, because if this is positive, that is negative. In this case, it's inverted. That's how you interpret all of these answers. Hope that helps. Let's look at the next question. Calculate the angle of minimum deviation. So we need to calculate the angle of minimum deviation. Let me write what capital D is. Produced by an equilateral prism. It's an equilateral prism. That means the angle of the prism is 60 degree. So that's the angle of the prism. Of refractive index 1.65. Refractive index of the prism, my dear friends, is 1.65. We need to find the angle of minimum deviation. Such a direct question. Let's try to substitute and get the answer. The refractive index of the prism, my dear friends, is given by ratio of sine of A plus D divided by 2, the whole thing divided by sine of A by 2. That's how you calculate the refractive index of the prism. Let's substitute. We have sine of A plus D, which is 60 plus D divided by 2 divided by sine of A by 2. A is 60 degree divided by 2. The refractive index of the prism is 1.65. Right? So let's find out what sine 60 plus D by 2 is. Sine of 60 plus D divided by 2 is equal to 1.65 multiplied by sine 30, because sine 60 by 2 is sine 30 is 1 by 2, right? So what does 60 plus D divided by 2 become equal to? It becomes equal to sine inverse of 1.65 plus, 1.65 into 1 by 2, and that basically is 0.825. 0.825. Well, just do the calculation and you should get that. What is sine inverse of 0.825? The sine inverse of 0.825 turns out to be 55.6 degree. Then what is 60 plus D? 60 plus D, my dear friends, becomes equal to 111.2. Well, what is D then? D, my dear friends, becomes equal to 51.2 degrees. That is the angle of minimum deviation. Quite a simple question, quite a direct question. All that you have to do is find sine inverse of that number and you should be able to get the answer. Let's look at the next question. Let us look at the next question. At what angle should a ray of light be incident on the face of an equilateral prism so that it just suffers total internal reflection at the other face? That's the question. The refractive index of the material of the prism is 1.5. We know the refractive index of the material. We know that it's an equilateral prism, and that's all we know. Let's try to figure out. Quite an interesting question out here. Let me first draw out a prism. So here I have a prism. Let's color it up so that it looks a little better. So that's our prism. I have a ray of light that is hitting the prism at an angle of incidence I. To measure that, we will also draw a normal. So here goes the normal. So that's the normal. A little misplaced, we will move it, not a problem at all. That angle of incidence, my dear friends, is I1, if you like it. The ray of light is now going to undergo refraction, and because of which it's going to bend. Let's say it bends like this. Okay. The normal here also shall be drawn. Let's say this is the normal at that place. The ray of light is now going to undergo refraction. It's going to bend away from the normal. But the question says that it graces the surface of the two media, because the question says it just suffers. That means the incident ray, dear friends, is at the critical angle. So this angle happens to be the critical angle. See. We have usually called this angle R1. So let's continue to call it R1. That is the angle of the prism. The angle of the prism is A, and we know it's an equilateral prism, so A is 60 degrees. So that's a known information. 60 degree. A is 60 degree. Now let's do some reverse engineering. This is refractive index of the prism. We know that it is 1.5. It's given in the question. N is my friends, NP is 1.5. Because nothing is given in the question about the refractive index of the surrounding medium, I'll assume that to be air, and the air's refractive index is 1. Let's apply Snell's law for that refraction. How do you do that? NP sine C is equal to NA sine 90. That's 90 degree out there. So let's do this. NP sine C equal to NA sine 90 degree. That is the equation. NP, my friends, is 1.5. Sine C, C has to be figured out. NA is 1. Sine 90 also is 1. Well, what does sine C become equal to? Sine C, my friends, becomes equal to 1 divided by 1.5, which is 0.6666. That's sine C. What is C? C is sine inverse of 0.6666. It turns out to be 42 degrees. Nearly that. Okay, 42 degrees. We know the critical angle now. But you know what? Angle of the prism, the angle of refraction inside the prism, and angle of incidence inside the prism. A, R1, R2. R2 is now in this case C. They have a relation. We are quite well aware of that. So A, my friends, becomes equal to R1 plus C for that matter. If you want to know what is R1, which is essential to find I1, we can simply figure out what's R1. It is A minus C. A is 60 degree because it's an equilateral prism, and C is 42 degree. This turns out to be 18 degrees. R1 is 18 degree. Once we know that R1 is 18 degree, we apply Snell's law for the first refraction. And what does that become? NA sin I equal to NP sin R1. Because this is also I1 and that's R1. NA is 1, my friends. Sin I1 is equal to NP, which is 1.5, multiplied by sin 18 degree. The product turns out to be 0.4635. 0. Oh, this is 1.5. I'm so sorry. I think quite a few things went haywire. Right. All right. There we go. Fine. So we have the product sine 18 degree. You have to use the Clark's table and get the answer. Multiply this, and this turns out to be 0.4635, and sine inverse of 0.4635 is going to be somewhere near 28 degrees, and that's your answer. Nearly 28 degrees. Well, that's how you crack that question. Well, we found the angle of critical angle using the relation between A, R1 and C. We found R1, and once you know R1, apply Snell's law and get the answer. An important question for the board exam. And with this, I think we have solved almost all possible questions with the board exam. So make sure that you practice all of these to develop proficiency, and you will be able to answer your board exam confidently. Remember, the day you stop growing is the day you start decaying. Thank you so much.